All right, so we are going to look at continuing on with learning how to write chemical equations. So you actually looked at chemical equations when you were in grade 10. You looked at types of chemical equations. I just want to remind you of just some of the terminology that's around writing chemical equations. So we're pretty specific in chemistry with how we actually like to write chemical equations. So I want to make sure we're all on the same page. So what a chemical equation is it's a short description of a chemical reaction. It's very similar to mathematics, where they have a certain structure you have to follow. That's because we're actually going to be doing math around them. Unit 3, we're going to be looking at applying math to these chemical equations. So you always want to make sure you use kind of the same terminology. So you always want to have what we call reactants on the left. Remember, a reactant is anything that goes into a reaction, and you want to have anything that comes out of a reaction, your products on the right. So I always like to think of chemistry as baking chocolate chip cookies, maybe just because I really like cookies. But I always like to think of the reactants of chocolate chip cookies as like your ingredients. So your chocolate chips, your flour, your sugar, whatever else goes into chocolate chip cookies would go over here as reactants. And your products would, of course, be your chocolate chip cookies. Now, sometimes you're going to have more than one reactant. Sometimes you might have multiple reactants. Sometimes you might have more than one product. So in order to separate out different reactants and different products, we use a plus sign. So if there are more than two reactants, there won't always be, but if there are, you use a plus sign between those two reactants. Now, a question here that students normally ask me, does it matter what reactant you list first? Absolutely not. There's no rule around it, no alphabetical order, nothing like this. Whatever reactant you want to list first is fine, as long as there's that plus sign between here. Same idea with the products. If we do have more than one product used, we use a plus sign as well. This arrow here, this is what we use to say yields. It's not equals. People always say hydrogen plus oxygen equals water. We don't use the word equals in chemistry. We use the word yields. So this arrow just means yields. It's like the actual symbol for the chemical reaction happening. So your reactants are going to combine. This little bit of magic is going to happen. You're going to have this yield symbol, and your products are going to form. Now, this is something new that you actually haven't seen. I want to introduce this idea to you because we're going to talk about it a lot in grade 12 chemistry. So I want you to see it now so you understand what it means. We can actually sometimes have something called a reversible reaction. So what that means is you can have a reaction go in both directions. It can go in this direction or in this direction. So maybe your reactant 1 and reactant 2 combine to form your product, and then your product can also break down to go in the other direction and go back to your reactants. So if that happens, we have this reversible arrow here. It just means the reaction can proceed in either direction. So we're going to see a couple this unit that I'm going to show you just so you get used to them. But it actually has a whole unit in grade 12 chemistry to itself called equilibrium that we're going to look at reversible reactions. All right, so just a reminder of what a reactant is and what a product is. Now you can see. A reactant is used up during a chemical reaction. So you always use up your reactants. That's your ingredients. And a product is always created or formed during a chemical reaction. So reactants on the left, they're used up. Products on the right, that's what's being formed. We have a couple of general equation types. So these are just different types of equations that you can actually see. Again, we're going to talk about them in more detail as we come up to them. But this is an important foundation for grade 11 and grade 12 chemistry. So one type of reaction you can have is called a spontaneous reaction. We're going to be looking at mostly spontaneous reactions in grade 11 chemistry. A spontaneous reaction occurs without any special conditions or energy required. So actually, up until this point, you've only looked at spontaneous reactions that you know of. You've looked at reactions that look like this, where you have a reactant on the left and a product on the right. And as long as the reactants are present, the second that you add the two reactants together, your product is going to form. So think about grade 9 and grade 10 chemistry. You poured two things into a test tube, your product formed. That was an example of a spontaneous reaction. So you didn't have to have anything else present. A non-spontaneous reaction is something we're going to look at more detail in grade 12, but we're going to start introducing them in grade 11. A non-spontaneous reaction requires what we call a catalyst. So they require some sort of other special ingredient to allow that reaction to happen. That catalyst could be another chemical. That catalyst could be heat. Sometimes that catalyst has to do with UV light as well too. So a non-spontaneous reaction requires something else to be present. I'm going to show you how to represent a catalyst in just a second. You can also have exothermic and endothermic reactions. I did start using these terms in grade 9 chemistry and also grade 10 chemistry to get used to them, but you don't really need to know what they mean until now. So we're going to now separate out reactions into exothermic or endothermic. We're going to study exothermic reactions today. An exothermic reaction is we're going to study a special type of exothermic reaction today. An exothermic reaction is where heat is produced or given off. So essentially in an exothermic reaction, you're always going to see heat given off as a product. You've actually seen exothermic reactions already in grade 9 and 10. An exothermic reaction is anything that feels hot. So think about in grade 9, we had you feeling test tubes and you were describing if the test tube felt hot or cold. If it felt hot, that was an example of an exothermic reaction. Heat's given off, so it feels warm to the touch. An endothermic reaction is just the opposite. An endothermic reaction means that heat is required or absorbed. So it means that energy is being taken into the reaction. In that case, your test tube is going to feel cold. So if you think in grade 9 and 10 feeling the test tubes and they felt cold, that's because it was an example of an endothermic reaction. All right, so a catalyst is a substance that can speed up or force a chemical reaction. So before up here, we talked about those non-spontaneous reactions. Non-spontaneous reactions use a catalyst. So these are all things that might help to force a reaction to happen. A catalyst is actually neither a reactant nor a product. So a catalyst is not going to be used up. It's not necessarily an ingredient. A catalyst isn't going to be formed, so it's not necessarily a product. A catalyst is essentially just there in order to make the reaction happen. It's not a participant. So a catalyst might be a certain chemical, and I'm going to show you now how to actually represent these catalysts in a chemical reaction. So in a chemical reaction, you're going to represent your catalyst. You're actually going to place it on, ooh, that's not a very straight arrow. That's okay. You get the point. You're going to place it on top of your yields arrow. So since a catalyst isn't a reactant, a catalyst isn't a product, you're actually going to place it right on top of this arrow, and that's going to tell you that the catalyst, that it's a required catalyst, it's not used up in the reaction. So a catalyst might be a specific chemical. An example of a chemical catalyst might be sulfuric acid. So in grade 12, if you take grade 12 chemistry, you're going to be doing a lab with me that requires very concentrated sulfuric acid in order for the catalyst to form. So if your catalyst is a chemical, all that you would do is you would just list the chemical right on top of the yield zero, and that tells you that in this case, H2SO4 or sulfuric acid is a catalyst. If heat is required, same idea, you're just going to go ahead and you're going to place it over top of the arrow, and usually the symbol for heat is this little triangle. So you actually might have seen this in grade 9 or grade 10. Sometimes I'll write my chemical reactions like this. You're going to see in this unit, I'm going to have triangles over top sometimes. That triangle just means that heat is a catalyst. Heat is required to make that reaction happen. UV light, so that's coming from the sun. Sometimes UV light is required. And in that case, you're just going to go ahead and list UV over top of the arrow. And sometimes a certain pressure is required. So we're going to talk more about pressure in the last unit. If there ever is pressure required, you would actually list specifically the amount of pressure. So for example, if there's 10 kilopascals, kilopascals is the unit for pressure. If there's 10 kilopascals of pressure required, you would list it right over top here. So a catalyst is always listed over top of the arrow, and you pretty much just list whatever the catalyst is. All right, now that we've covered catalyst, I want to talk a little bit about the state. So I'll move my face down here. There we go. So each time that you have a reactant or a product, you want to make sure that you include the state of matter as well too. So getting into this unit, I'm going to be either telling you the state or you're going to be required to know the state on your own. So if it's a weird state, if it's really hard to predict and it's a compound, I'm going to tell you what the state is. However, if it's ever just an element from the periodic table, you can automatically tell what the state is yourself, and that's by using the periodic table. So remember, on the periodic table, the one in our room, anything that's blue is a liquid, anything that's red is a gas, anything that's black is a solid, or it might have that symbol of that little square, that little water droplet, or that little gas cloud. So any elements, you're actually told what their states are. Other than that, I'm going to help you in this unit to help to better predict what state there might be. For now, all I want you to know is what the states are. So there's actually 4 states that a substance can be in a chemical reaction. The first state is a solid. So if it's a solid, you use an S. If it's a liquid, use an L. Oftentimes, you're going to see, we'll actually sometimes use this cursive L instead. So oftentimes when something is a liquid, I'll list it like this instead. The reason that we use this cursive L is it just can't be confused with a 1. So this here looks a lot like a 1. If we do this cursive L, we definitely know it's not a 1. A gas is a G, and then aqueous. Aqueous might be a new concept for you. So what aqueous means, the definition is down here. It means a substance that's dissolved in water. So if we have a solid that we then add water to, so for example, if you take a bunch of table salt and you dissolve it into water, that would be an example of an aqueous solution. Aqueous solutions are actually very common in chemistry, and we're going to have a whole lesson talking about aqueous solutions this unit. Now, we're very picky in chemistry where you put this state. So this state actually has to be as a subscript. So for example, if you're trying to tell me that carbon is a solid, you have to list it, little tiny subscript, as an S with the brackets. You don't want to have a big S with brackets behind, that's wrong. You don't want to have a big S with brackets in front, that's wrong. Your state always has to come after whatever compound it is or whatever element it is in brackets. So for example, if we're dealing with CO2, you'd have CO2, and then right after the O2, right after the 2 in the O2, you'd list G because it's a gas. And again, notice that this is a subscript. So I'm going to erase this. And as I erase this, you can actually see a couple examples of this below. I'm just going to scroll so you can see those examples. So you can see your examples here. Here we can see that salt sodium chloride is listed as a solid or aqueous or as a liquid. So sodium chloride can actually exist as these 3 things. So at room temperature, sodium chloride is a solid. So we know that at room temperature, table salt looks like salt. It's a solid. I think I have some. Good, I'm at my dining room table. So salt is right here, right? So you can see that it's a solid. Sodium chloride could also be aqueous. So if I took that salt and I dissolved it into a cup of water, that sodium chloride is now aqueous. It's dissolved in water. So we would list it as aqueous. Or if we have a high enough temperature, I think you need about 800 degrees to make it happen. But if you have a high enough temperature, you could melt sodium chloride. We call that molten sodium chloride. And at that point, it'd be a liquid. So technically, a substance can exist at any of the states. It will have a typical state that it exists at room temperature. And then you could change the states by either adding or taking away energy. So pretty much you always want to tell me the state, just so we know what we're dealing with at the time. Last up, we want to talk about the difference between word equations and actual skeletal equations. So again, this is kind of where you left off in grade 10 chemistry. So on your grade 10 chemistry unit test and on your grade 10 exam, you would have had to go through and list word equations and convert them to chemical equations. So word equations are nice because they're easy. So in a word equation, you're identifying the reactant and the product by the name only. So for example, you're going to go ahead and tell me that iron and oxygen is combining with iron 3 oxide. So the nice thing here is that you don't necessarily have to know what the chemical symbol for iron is. There's no numbers involved, and it's much easier to say, right? Iron plus oxygen equals iron 3 oxide. Another example, copper plus silver is going to yield silver silver and copper 2 nitrate. So there I tried to make sure I had the right terminology for you too. So notice instead of saying plus, I said and. So copper and silver nitrate. And instead of saying here arrow or equals, I try to say yield. So copper and silver nitrate will yield silver and copper 2 nitrate. On the other hand of that, you can have what we call skeletal equations or skeleton equations. These are actually way more valuable in chemistry, but they're harder to write. So a skeleton equation is a chemical equation in which the products and reactants are represented by their chemical formulas. So this first skeleton equation here is actually our first word equation we gave you up here. So rather than writing iron plus oxygen, we wrote the chemical symbol for iron. Note that we put the state there as well too. We wrote the chemical symbol for oxygen. Remember, Hofbrinkel always has to apply. So anytime you're writing an element by yourself, you want to ask yourself, is it Hofbrinkel? So we put this little 2 here, and then we had a gas. This should have an arrow between it. So let's pretend like there's an arrow between it. And then we put the chemical symbol for iron 3 oxide. So this is a chemical symbol for iron 3 oxide. Notice that the states are present for all of them as well too. This is the same as our second word equation. So copper, solid copper, plus silver nitrate is going to yield copper, solid, or silver, solid silver, and copper 2 nitrate. So you can see these are a little bit more challenging to write. You actually have to take the name and you have to convert it to the chemical formula. We did this in Unit 1, so you should be okay with this, but it takes a little bit more time. The really nice thing here, though, is that you can actually see how many atoms you have, which is way more useful in chemistry. So I can see that on this side, I have 2 atoms of iron and I have 3 atoms of oxygen, whereas on this side, I only have 1 and 2. So you can actually see where the atoms are. Remember that chemistry is just rearranging the atoms. So we're just taking this iron and this oxygen and we're rearranging them in a different way. So this is way more useful because you can see the number of atoms. This is also going to lead into our next lesson, which is our little bit of review, which is balancing. So if you write a proper skeleton equation, you can see, are the atoms equal? If they are not, you are going to have to worry about balancing. So why don't you go ahead and join us for our next video. In that video, we are going to remind ourselves on how to balance chemical equations. I do have a bit of homework here that I want you to try using your textbook. This homework is just going through and it's helping to remind you how to write these chemical equations. Pretty much everything we do from now on out in grade 11 and grade 12 chemistry is going to all be chemical equations. So you need to make sure you're really good at writing these. So try your homework and we'll see you in the next lesson where we talk about balancing. Have a great day. See you later.